Section 5.6, Integrals involving exponential and logarithmic functions. In this section, we're going to focus on integrals that involve exponential and logarithmic functions. Recall that we have the following two basic integral rules. The definite integral of e to the x is e to the x plus c, and the definite integral of 1 over x, which is the same as the definite integral of x to the negative first, is the natural log of the absolute value of x plus c. Recall that x to the negative first is the only power function that we cannot apply power rule to. So we do have to be a little careful with x to the negative first or 1 over x, making sure we remember its antiderivative is the natural log of the absolute value of x. Thanks to the substitution technique we learned in the last section, we can show that the integral of a to the x is a to the x over the natural log of a plus c. Recall when we were deriving the derivative rule for a to the x, that we can rewrite a to the x as x natural log of a. So through our substitution, we can make u equal x natural log of a. Keep in mind natural log of a is just a number since a is constant. We get that du equals natural log of a dx, where du equals natural log of a equals dx. So now we can substitute, and we get the integral of e to the u times du over the natural log of a. Dividing by the natural log of a is the same as multiplying by 1 over the natural log of a, which would be constant, so we can kick that out of the integral. Antiderivative of e to the u is e to the u, and then we can plug our u back into place. And then we can rewrite the e to the x natural log of a back into a to the x. And there is our integration rule derived. Now we're going to evaluate the definite and indefinite integrals. We're going to start with the integral from 0 to 4 of e to the negative square root of x over the square root of x dx. Here we are evaluating a definite integral. And we can see that our integrand is not one of the basic functions that we know a simple rule for. So we're going to try to use substitution. To help us with our substitution, let's first rewrite our square roots with exponents. So each square root we'll rewrite as x to the 1/2 power. Here I need to pick an expression for u. Since I see negative x to the 1/2 as my exponent to e, I'm going to try making that my u. So we'll set u equal to negative x to the 1/2. Now we'll find our du, and we get that du equals negative 1/2 x to the negative 1/2 dx. Since we don't have a negative 1/2 in our integrand, we can multiply both sides of our differential by -2, and we get that -2 du equals x to the negative 1/2 dx. I also don't see an x to the negative 1/2 in my integrand, but I do see an x to the 1/2 in the denominator of my integrand. So we should rewrite the x to the negative 1/2 we have right now in our differential, so that way it doesn't have negative powers. And that becomes 1 over x to the 1/2 dx. Now let's start substituting the integrand before we start changing our bounds. Our e to the negative x to the 1/2 is going to become e to the u. Since we have the x to the 1/2 in the denominator, that is the same as 1 over x squared, because divided by x to the 1/2 is the same as multiplying by 1 over x to the 1/2. So that is going to be replaced by -2 du. So our integrand becomes -2 e to the u du. Since we were able to rewrite our integrand completely in terms of u, we can now go ahead and change our bounds. Our upper bound was x equals 4, and when we plug that into our substitution, we get that our new upper bound is u equals -2. As for the lower bound, which for x's was x equals 0, plug that in to our substitution, and we get that our new lower bound is u equals 0. So now we need to evaluate the integral from 0 to -2 of -2 e to the u du. The antiderivative of e to the u is e to the u, and we're going to evaluate from 0 to -2, plug in our bounds, and then we can simplify. Recall that e to the 0 is 1, -2 times 1 would just be +2. So we get that our definite integral equals -2 e to the negative second plus 2, or 2 minus 2 e to the -2 if you want to rearrange the order to make it look nicer. Next, we're going to evaluate the integral of x squared, 3 to the x cubed. Since we don't have bounds, this is an indefinite integral, which means we're trying to find a family of antiderivatives. Looking at the situation, we see this x cubed as a power of 3, so let's try making that our substitution. So we'll make u x cubed, which makes du equal to 3x squared dx. Divide over the 3 since we don't see it in the integrand, and we get du over 3 equals x squared dx. Now we can do the substitution, and our integrand becomes 3 to the u, du over 3, and we can kick out 1/3 from our integral. We can rewrite it as 1/3 times the antiderivative of 3 to the u du. As for the antiderivative of 3 to the u from the previous slide, that is 3 to the u over the natural log of 3. And since this is a indefinite integral, we do need to remember the plus c. Clean up our antiderivative a little bit more and replace the u with the x cubed. And we get 3 to the x cubed all over 3 natural log of 3 plus our constant c. Now we're going to evaluate the definite integral from 0 to pi of sine of x times 2 to the cosine of x. Since we're evaluating a definite integral, we don't have to worry about the plus c. And when we do the substitution, we'll change our bounds. So that way, we don't have to worry about replacing our u back with our substituted expression. Here, I see cosine x as the exponent of my exponential function, so we're going to make u cosine x. So our du would be negative sine x dx. Since we don't see a -1 as a factor of our integrand, we'll multiply it over to the other side, and we get that negative du equals sine dx. Before we change our bounds, let's check to make sure our integrand can be written in terms of u. The 2 to the cosine x becomes 2 to the u. The sine x times dx becomes negative du. Now we can change our bounds. Our upper bound for x was pi, which means our new upper bound for u will be cosine of pi, which is -1. As for the lower bound, for the x's, that was x equals 0, which means for u, that'll be cosine of 0, which is +1. So we have the integral from 1 to -1 of 2 to the u times negative du, which is the integral from 1 to -1 of -2 to the u du. The antiderivative of 2 to the u is 2 to the u over the natural log of 2, and we're going to evaluate with our bounds from -1 to 1. And when we plug in our bounds and simplify, we get -1 over 2 natural log of 2 plus 2 over natural log of 2 as the value of our definite integral. Now we're going to evaluate the indefinite integral of 4 times 5 to the x times the square root of 2 minus 5 to the x dx. Now this problem is a little bit different compared to the last three we just did. In the last three, we made our u the exponent of our exponential expressions. But here, we see the 2 minus 5 to the x trapped inside the square root. So here, I'm going to make that my u. So with u being equal to 2 minus 5 to the x, that's going to make du 5 to the x natural log of 5 dx. Since we see the 5 to the x and the dx in the integrand, we'll divide both sides by -1 natural log of 5, and we get that negative du over the natural log of 5 equals 5 to the x dx. Now we can proceed to substitute. The 4 in the integrand stays as is since there's nothing to substitute it away. The square root of 2 minus 5 to the x becomes the square root of u, and the 5 to the x times dx, that becomes negative du over the natural log of 5. The 4 and the -1 over natural log of 5 are all constants, so we can kick them out of the integral. The square root of u we'll rewrite as u to the 1/2. The antiderivative of u to the 1/2 and simplify, and we get -8 over 3 natural log of 5 times u to the 3/2 plus c. Since this was an indefinite integral and there were no bounds to change, we're going to replace our u with the expression that u was used to substitute for, and we get -8 over 3 natural log of 5 times 2 minus 5 to the x, all raised to the 3/2 plus c as our antiderivative. Now we're going to evaluate the definite integral from 3 to 5 of 3x squared plus 1 over x cubed plus x. Integrals involving natural logs can be a little tricky to evaluate. With an expression like our integrand here, we don't really immediately see a function trapped inside of another function. So what we'll try to do is we'll make our denominator the u, and we get that our du is 3x squared plus 1 dx. Now let's see if this substitution works. So checking to make sure our integrand can be written in terms of u, our denominator is what we made u. As for the numerator, 3x squared plus 1 and dx are du. So we have the integral of du over u. Since we were able to rewrite our integrand in terms of u, let's change our bounds. Our upper bound for x was x equals 5, which means u would be 130. Our lower bound was 3, which means our new lower bound will be 30. So now we have to evaluate the integral from 30 to 130 of du over u. Du over u is a common way of writing 1 over u du. Whichever form you look at, du over u or 1 over u du, both of those are natural log rules, not power rules, because 1 over u is the same as u to the -1st, and -1 powers do not work for power rule. So the antiderivative of 1 over u is the natural log of the absolute value of u, which we'll evaluate from 30 to 130, plug in our bounds, and we get the natural log of the absolute value of 130 minus the natural log absolute value of 30. Evaluate our absolute values. Since we're taking the absolute values of positive numbers, the absolute values of those numbers would be themselves. And from there, if you do want to simplify further using our logarithmic properties, since we are subtracting two logs, we can write it as a single log dividing their inputs and then reduce, and we get that our definite integral equals the natural log of 13 over 3. Now we're going to find the indefinite integral of 3e to the x all over 5e to the x plus 1. Very similar to the last problem, let's try to make our u the denominator 5e to the x plus 1 since we don't see anything else trapped in an expression. That means our du would be 5e to the x dx. And just like before, we can divide over the 5. And we get du over 5 equals e to the x dx. Now let's substitute the denominator 5e to the x plus 1 becomes u. The e to the x in the numerator with the dx, that becomes du over 5. And we still have 3 left over in the numerator. Since 3 and the 5 are constants, and divided by 5 is the same as multiplying by 1/5, we can kick 3/5 out of our integral, and the antiderivative of 1 over u would be the natural log of the absolute value of u. Now we can replace our u with the 5e to the x plus 1, and we get that our antiderivative is 3/5 natural log of the absolute value of 5e to the x plus 1 plus c. If we look a little bit more carefully, e to the x is a positive function. No matter what I plug in for x, it is going to be positive. So 5e to the x would also be positive since positive times positive is positive. And if I add 1 to a positive function, it's going to stay positive. So 5e to the x plus 1 is a positive function. The reason why this is important is whenever we take the absolute value of something positive, it is itself. So the absolute value of 5e to the x plus 1 is just 5e to the x plus 1. So our antiderivative simplifies a little bit farther to 3/5 natural log of 5e to the x plus 1 plus c. Now we're going to find the definite integral from 1 to e to the pi of sine natural log of x all over 2x. Unlike the previous examples, we can clearly see an expression trapped inside of a function. Here we see the natural log of x within the signed function. So we'll try making that our u. So if u equals the natural log of x, du would equal 1 over x dx. Now let's start substituting into the integrand to see if our substitution works. The sine natural log of x becomes sine u. The 2 has nothing it can be replaced with, so we'll keep the 2. As for the x in the denominator and the dx, these two are the same as 1 over x dx, since dividing by x is the same as multiplying by 1 over x. So the dx over x can be replaced with du. So our integrand does become sine u over 2 du. So now that we've written our integrand in terms of u, let's change our bounds. Upper bound for x's was e to the pi. So our new upper bound would be the natural log of e to the pi, which would be pi. Next, our lower bound was x equals 1. So our new lower bound would be u equals natural log of 1, which is 0. Now with our bounds changed, we can find our antiderivative. Our antiderivative would be negative cosine u over 2, which we're evaluating from pi to 0. And when we plug in our bounds and simplify, we get that our definite integral is equal to 1. Next, we're going to evaluate the definite integral of 1 over x times log base 2 of x to the third power. Looking at our integrand, we can see that the log base 2 of x is being raised to the third power. So let's try making that our u. So we'll make u equal to the natural log of 2x, which makes du 1 over x natural log of 2 dx. Since natural log of 2 is just a constant and we don't see it as part of the integrand, we can multiply that to the other side, and we obtained that natural log of 2 du equals 1 over x dx. Now we'll proceed to substitute. The log base 2 of x cubed becomes u cubed. The numerator will stay 1. As for the x in the denominator and dx, because our natural log of 2 du equals 1 over x dx, the x in the denominator with dx becomes natural log of 2 du. Since the natural log of 2 is just a constant, we can kick that out of the integral. And as for the 1 over u cubed, since it's not 1 over u, we can rewrite with the negative exponent and apply power rule, since negative 3 is a power that we can use the power rule for. Remember, it's only negative 1 where we can't apply power rule. So when we apply power rule, we get that the antiderivative of u to the negative third is u to the negative second over negative 2. Replace our u with the log base 2 of x, and we get natural log of 2 times the log base 2 of x to the negative second all over negative 2 plus c, which we can further clean up, and we get negative natural log of 2 times the log base 2 of x to the negative second all over 2 plus our constant c. So one thing to be careful of when we're doing integrals involving logarithms, sometimes the entire denominator may be our u, sometimes just part of the denominator will be our u. The important thing to try to do first is look for any expression trapped in a power. Try to see if that will work for our substitution. If it does, great, proceed to find your antiderivative. If not, try another substitution, maybe manipulate your u or your du to try to make things fit. Next, we're going to find the indefinite integral of x cubed plus x minus 1 all over x plus 1. This problem has a few different methods that we could use to try to integrate this. If we try to make our denominator u, like we have in previous problems, we would have u equals x plus 1, which means du would equal 1 dx or just dx. Now, I could try to plug things in, because remember, I can manipulate our u, and we would get x equals u minus 1. And this would be important here, because the x cubed and the x in the numerator are not part of my du. So I would have to manipulate my substitution to make things fit. But here comes the problem if I try to substitute. Our integrand would become u minus 1 quantity cubed plus u minus 1 all over u. Well, yes, my integrand is entirely in terms of u. I would now have to expand that u minus 1 to the third power, which might be rather difficult to do. Instead, we're going to take a different approach to this problem to make it a little bit easier. So if we reset the problem and take another look at the integrand, notice how our numerator is degree 3, while our denominator is degree 1. Whenever we're trying to integrate a rational function and the degree of our numerator is higher than the denominator, one thing we can do to try to simplify the problem is we can perform polynomial division to try to rewrite the integrand. If you need a refresher on polynomial division, please take a look at the pre-calculus videos for Unit 1. But going through the polynomial division, we get that x cubed plus x minus 1 all over x plus 1 is equal to x squared minus x plus 2 minus 3 over x plus 1. So now we can rewrite our integrand. So our integral becomes the integral of x squared minus x plus 2 minus 3 over x plus 1. What's great about this is our first three terms are a polynomial, which are really easy to integrate. So we'll put that in one integral. As for the negative 3 over x plus 1, we can kick the negative 3 out and put the 1 over x plus 1 in its own integral. Working out the integral of the x squared plus x plus 2, just applying power rule one term at a time, we get x cubed over 3 minus x squared over 2 plus 2x. As for our last remaining integral, we can evaluate that by making u equal to x plus 1. So our second integral becomes negative 3 times the integral of 1 over u du, and the antiderivative of 1 over u is the natural log of the absolute value of u. Now that all my integrations are done, I'll place my plus c, and as for my final answer, we'll replace the u with x plus 1. And x plus 1 can be positive or negative, so we do have to keep the absolute values. But notice how with the polynomial division, we were able to avoid very long tedious expansion and collecting like terms, which does make the integral a little bit easier.